Thank you for giving me opportunity to introduce Dr. B.N. Sharma, sir. Dr. B.N. Sharma, scientist engineer G from Space Application Center, Ahmedabad, has more than 26 years of experience in system design and development of a variety of electro-optical sensors for ISRO's Earth observation and planetary missions. He joined SAC-ISRO in July 1997 after completing his Master of Science from Pandit Ravi Shankar Shukla University, Raipur, Chhattisgarh. Since his joining, he has been part of teams that develop various flagship EO sensors for India's space program, including ResourceSat, OceanSat, CartoSat, and Chandrayaan series missions. He has developed various systems and methods for sensor design, simulation, testing, and characterization of EO sensors. He completed his PhD in science from Nirma University, Ahmedabad. He has been recipient of ISRO's Young Scientist Award and ISRO Team Awards. He has published his work in several conference and peer-reviewed journals. His research interests include sensor system design, configuration study, sensor simulation, integration, testing, characterization, and calibration of electro-optical sensors. Now I requesting Dr. B.N. Sharma sir to present on hyperspectral missions.
Yeah, thank you, Hriday. And first of all, I take this opportunity to thank the ISRO headquarter team, the STAR team, who has given me this opportunity to present on the optical hyperspectral imaging systems. And I welcome all the participants who have joined online. So I will start my presentation. I hope that the presentation is visible to all the participants. Now, as the title of my presentation is about the optical hyperspectral imaging system, so I tried to organize my presentation in following way. That first of initially, I will give a small brief introduction of hyperspectral remote sensing, what it is and how it works basically. And then we'll touch upon some of the spectral properties of some important earth materials which our sensor is going to observe from space. And then once we understand this, then we will go into the deep into the hyperspectral sensor technology elements. What are the elements which enables us to monitor the Earth's feature in different spectral regions with a very finer spectral resolution. Then in order to understand the sensor technology and their capability, we need to know some of the important spectral sensor performance parameters that I will briefly describe to the audience. And then I will touch upon the important hyperspectral sensors which we have developed at SAC-ISRO. And then at the end, I will give a brief introduction about some of the imaging applications which are being used globally, also with the ISRO community. So moving on to the presentation, I understand that the previous lectures would have touched upon about the remote sensing and other aspects. So briefly, I will tell about remote sensing. As the word suggests, remote sensing is basically we sense something from remote. So like we are trying to understand the feature of Earth using a different platforms. So why these platforms? These platforms are important because they give us perspective. Like if I try to observe some of the features or phenomena from a very close quarters, I may not be able to get a bigger perspective of the phenomena and the effects. So generally we become airborne and spaceborne to observe large areas of Earth and then try to interpret what is happening physically on the Earth. So we all know that we call these satellites as eyes in the sky. So I need not dwell much on this. So there are, as I have shown in this figure, in the right side figure, there can be two possible platforms. There can be many, but I'll be touching upon these two possible platforms. One is the airborne, which is aircraft-based observations, and also the spaceborne observation techniques. So basically, in this technique, what we do, we observe the ground reflectance, target reflectance values, so that we can interpret the properties of the ground targets. So now the core of this remote sensing technology is the electromagnetic radiation. We are all aware that the electromagnetic radiations interact with the matter, and that interaction we try to observe with our instruments. So in any electromagnetic radiation, there are two important fundamental properties, that is the frequency and wavelength. They are correlated. So in the next slide, I will show how this electromagnetic spectrum covers a very large spectrum. So if you see the center part where the ultraviolet, visible, and thermal IR are mentioned in bold letters. So this is our area of interest in the optical remote sensing domain. So here the wavelengths span from somewhere around 200 nanometer in UV to around 400 nanometer. Then in the visible range, I will give more details about the quantitative numbers, what kind of wavelengths these regions are covering. So here I just wanted to highlight that the electromagnetic radiation encompasses from cosmic rays to radio and TV waves, etc. So if we see, our interest is basically in the optical remote sensing domain, where we cover visible, infrared region. Also, there is something called microwave region, which some subsequent presenters will be covering on this. So my focus will be mainly on the optical remote sensing. So in visible range, we can see lots of colors we try to cover, and so they start from red, orange, yellow, the vibgyor we all know. So these are some of the typical bands where the light, the solar light interacts with the matter, and we get the reflected light from these targets, and our sensor sees those reflected lights in these bands. Similarly, if you go to infrared region, so we call it as a near infrared region, which is spanning from 0.7 to 1.5 micron. Then after 1.5 micron to 3 micron is called a short wave infrared region. This is again where the solar spectrum contains up to this 3 micron range. So what we observe is from the reflected sunlight from the sun in our sensors. Once we move to higher wavelengths, that is mid wavelength infrared region, which is MWIR, which is spanning over 3 to 8 micron. So here all the emission starts. These are basically the emission characteristics of the targets. So depending upon the target temperature, we will be getting different emissions in these spectral range, that is covering MWIR as well as LWIR range from 8 to 15 micron. And also there are certain targets which emit in far infrared ranges also. So I will be talking about the optical sensors which are covering to these spectral range, that is from visible to NIR, SWIR, and MWIR, LWIR, etc. Now, as we all know, sun is the basic source for any optical sensor. So the sun irradiates the ground targets, and depending upon their spectral characteristic, these targets reflect back the solar energy to our sensor, which is sitting on a satellite. So basically, in the remote sensing, what we observe is generally the reflectance behavior of any target. So we generate a reflectance curve of that particular target, and that reflectance curve is nothing but the spectral signature of that target, because we know every target has a unique way of interacting with the light, and they reflect depending upon their internal properties. So if we can capture the reflectance curve of this object, we will be able to classify or identify these targets. So I've just shown an example, like the sun rays are falling onto a tree. The tree is having lots of leaves. So the leaves have cell structure. So in this cell structure, the light interacts, and depending upon their behavior, their absorption or reflectance behavior, the input light is reflected back towards the sensor. And this is how the sensor measures this reflected light. And then we will be able to tell about the state of this particular leaf in this tree. So like that, there are many other objects on the ground. It can be a concrete housing, roads, the pond, the water bodies, the mountains, and many other objects. So every object has their own fingerprints, spectral fingerprints, that we need to measure from satellites. So moving on. So basically in hyperspectral sensing, if you see, basically what is there in this hyperspectral sensing, we have to have another dimension, because any typical imager will be able to provide us a 2D image. So in 2D image, what we will see is the intensity variation. Although we may generate different colors, a colorful ground target picture we can generate, but they will be mainly showing the intensity variation in the two-dimensional way. But when we say hyperspectral, we get another dimension, that is, we try to sample these ground targets in a very fine spectral resolution. So we get a third dimension that is called as the spectral dimension. So by taking this two-dimensional image and adding spectral content into that, we'll be able to get hyperspectral data cubes. And these kind of imaging systems have got a lot of applications in geology, ecology, soil, and plant biology, camouflage detection, and also in atmospheric sciences. So our basic objective in hyperspectral sensing is not only to image the contextual information, also try to get the hyperspectral way, the spectral information of the targets. Now, just I have shown here typically how the hyperspectral cube looks like. You can see this is a two-dimensional picture on the top, and the third dimension is created here. So if you take out any one pixel, what we will see a stack like this, where one pixel will be having a spatial content, which is a contextual content, but in the other dimension, we will have the spectral content. For example, this area on this image corresponds to soil. So if I plot this spectral content in the x-axis as wavelength and the reflectance in the y-axis, I will see a typical spectral curve which will be representing soil. So by laboratory characterization, we know how the soil has a specific spectral behavior. So by remote sensing, we can match that with the laboratory observation, and we can tell that this particular picture element in this image is a soil content. Similarly, water and vegetation, all those things can be identified if we have got hyperspectral cubes like this. So now why hyperspectral? Why not multispectral or panchromatic? So I've just given you some example here. You can see the bottom side, there is one curve shown. So basically, this is representing one of the element taken which is called as elunite, and this has been, the spectra has been generated in a lab with a very fine spectral sampling. So you can see there are so many features in this spectral curve. But if we try to observe this, and the spectral behavior has been generated using a spectrometer which is having 5 to 10 nanometer spectral resolution. Now, the moment I see this particular spectral behavior in 10 to 50 nanometer spectral band, I will see something like this. And if I further degrade my spectral resolution to, let's say, 65 to 250 nanometer, this curve will look like this. So it will be becoming very difficult to identify this particular material, provided it has some overlapping features with some other material. So that is why hyperspectral is very important, which we will not be able to do with either a multispectral, which is lying from 10 to 50 nanometer, or a panchromatic bands, which are from 65 to 250 nanometer. So that is why hyperspectral technique is very important. Now, I have just tried to show it in more pictorial form rather than a curve form. So you can see here is a wide band panchromatic image where we can see the context information that it is covering some field. Now, if we add some multispectral, some color data into this, let's say 3 color RGB data, so I'll be able to see the RGB behavior, the color picture of this particular ground target. And if I add multispectral behavior, so I will be able to see some more information on this. But when I add hyperspectral, so this hyperspectral cubes will enable me to sample this ground target in much finer spectral sampling. So then I will be able to characterize these targets in a much better way. So basically, when we say hyperspectral is important, and why, what should be its spectral resolution? So when our spectral resolution reaches of the order of lambda by 100, so let's say lambda is in our visible range somewhere around 630 nanometer. So if 630 nanometer wavelength I'm trying to see, and my bandwidth is 630 divided by 100, so it's around 6 nanometer bandwidth if I get from an instrument, that instrument will be termed as a hyperspectral instrument. And anything above that, poorer than the 6 nanometer, will be termed either multispectral or a color photography or panchromatic images. So now with this brief introduction, let us move on to some of the spectral properties of some of the Earth objects. In this left left side graph, I've tried to show how a dry bare soil looks like spectrally. This x-axis is the wavelength, which is covering from 0.4 micrometer to 2.6 micrometer, and the y-axis is the reflectance observed from this particular target. So you can see there is a specific behavior of this dry bare soil, and this green curve shows the vegetation, how the vegetation, there is a great amount of absorption in this particular region, and there is the reflectance is very high, and we have got a steep slope here. So like this, there are some other features that I will explain in subsequent slide. Similarly, if I try to see the water, which has got a very low reflectance, and it is just covering in this visible spectrum range from 0.4 to, let's say, 0.7 micron. So these are the different behavior of different objects. So they form their spectral spectral characteristic of these targets, and they're basically the fingerprints of those targets, which we try to detect from the onboard satellites. So moving on to the next. So these are some of the other materials: the chlorite, aluminum-rich mica, then thermolite, dolomite, talc, and kaolinite. So these are some of the specific spectral behavior that we are trying to represent here. So our objective as a sensor design team is that we should be able to faithfully generate these spectral behavior so that we can classify these targets from any remote sensing images. Now, I'll just take one example and to explain how these spectral fingerprints are generated from any object. So let's say, let us take the example of vegetation. So why this specific spectral shape is seen from vegetation? So now, as we all know, the vegetation has a very high chlorophyll concentration. So chlorophyll at cell level, they try to absorb the visible radiation. So you can see here, there is a lot of drop in the reflectance. So all the light in from 0.4 to 0.68 micron is absorbed by that particular leaf, and we are not seeing any reflectance from there. But when we go to the, this is basically the leaf pigments. So pigment absorption happens. Once this leaf, we go to the cell structure level, so we see there is a lot of very large reflectance in the NIR range, that is spanning from 0.68 to around 1.3 nanometer. So we can see there is a very large reflectance from this in this wavelength region. Similarly, if you go to the higher wavelength region, that is the SWIR, which we call it as a short wave infrared region. So there we can see some specific absorption features. So these absorptions are basically from the water content present in the leaf structure. So this is how a particular ground target has its own unique spectral behavior. If we can measure this unique behavior, we will be able to characterize that target. Now, what is the significance? What will happen, like if I want to classify a target, let's say leaf in this case, so which is healthy, and as the season changes, and also there are some diseases on the canopy, so how this reflectance will change. So I've tried to show here some example like this. The darker green color is showing a healthy leaf spectrum, where we can see the absorption is happening in the visible region, a good amount of absorption. So that indicates there is a lot of chlorophyll present. So we can say it's a very live and a very good leaf, which is a healthy leaf. And then there is a transition happening into the NIR range. Now, as the color of the leaf changes, that color is basically indicating the degradation in the chlorophyll content. So as we go up, the chlorophyll content degrades. So that means the absorption reduces, so reflectance will increase. So we can see there is a continuous increase in the reflectance value. Also, we can see one specific feature here, that this edge, basically this edge, we call it as a red edge. So this edge is shifting towards blue. So as the chlorophyll content is decreasing in the leaf, my red edge is shifting towards blue. So this will indicate, if I am able to measure with any instrument the specific behavior of these canopy, I'll be able to tell that whether this leaf is healthy or unhealthy. So this kind of information we can derive from hyperspectral images. Yeah. So now this is what I talked about, was about the target characteristics. But when I see spectrum from target, the atmosphere comes in. So this is a basic atmospheric transmission curve. So we try to choose our bands in such a way that they are like in the transparent region of the atmosphere. You can see some atmospheric absorptions are happening. So we try to avoid observations in these spectral ranges. Okay, now coming to the hyperspectral sensor technology. Now these hyperspectral sensors can be deployed in different platforms. So depending upon the platform, only the configuration and the design of the hyperspectral sensor is done. So basically, I'll be talking about two platforms, the spaceborne and airborne, but there are some ground-based and portable lab-based for commercial applications. There are many hyperspectral sensors nowadays. It is being evolved. So from spaceborne, if you see some of the examples are InMap, Prisma. They are offering 30-meter spatial resolution, and they provide global and continuous coverage. This is the main advantage of spaceborne platform. You can have a global coverage. Also, you can cover a very large tract of land on the Earth. Similarly, when you go to airborne, you have IIRS-NG, which is a very famous hyperspectral mission by NASA. So there, the spatial resolution they are targeting is around 1 to 5 meter, and they are like on-demand kind of survey happens. So this is generally used in precision agriculture and disaster response management. There are ground-based sensors, which I'll not be talking about, but they are mainly basically for the field-based observations, where in a given field only the ecological and ecological evolution is monitored, and also they are used for satellite calibration also for that particular field. And the portable, there are many hyperspectral sensors commercially you will find, which provide sub-nanometer spatial resolution, and they are mainly used in factory environment for various food quality and forensic and diagnostic purposes. So now, in coming to I will be focusing mainly on the hyperspectral sensors from spaceborne platform or aerial platform. So there are 4 modes of acquisition possible for any hyperspectral sensor. One is shown in the left-hand corner, top corner, which we call it as a push broom line scanner. So basically, the satellite moves, and one particular line segment on the ground is spectrally separated, and the spectrum is recorded. And as the satellite moves, the subsequent lines are spectrally resolved. Similarly, there is something called whisk broom. So in this case, there will be one linear detector sitting onto the two-dimensional detector sitting onto the focal plane. So one row will record the ground swath, and the other rows will be giving the spectral information. Similarly, in the whisk broom, we have got maybe one detector, and then there will be scanning mechanism. So in this raster scan method, the entire Earth surface will be scanned, and the images will be generated. And there is something called snapshot and non-scanning method, where we can have a very snapshot image, and there will be some group of pixels. They will be representing number of bands. So across this detector area, we will have some group of pixels, and they will be giving the band information, spectral information. Similarly, there is something called staring scanning, where the satellite or the satellite is staring at one particular point only, and the spectral information is generated by rotating one filter wheel or by having some tunable filters in the optical path. Now, typically a hyperspectral sensor looks like this. Let's say there is a ground target, there will be a collecting optics, there will be a slit. This slit defines the spatial coverage of that particular target, and it limits the field. And once the light passes through the slit, there will be one dispersion optics. So this dispersion optics will be separating this input light into multiple wavelengths that our detector will be recording, which is sitting onto the focal plane of our sensor. So in this slide, you can see the heart of this hyperspectral sensor is the dispersion optics. All these other elements are anyway present in any of the imaging satellite. So now the heart of the hyperspectral sensor is, as I mentioned, is the spectral separation device. There are lots of spectral separation devices. So one is that grating base, which basically works on the diffraction principle. There is something called prism. We have all studied in our school and colleges, where the prism, dissects the input light into several 7 colors. And then there is something called tunable filters, where electronically these filters are tuned and the spectrum is generated. Okay, now as I've talked about the prism part, so prism basically provides us wavelength dependent refraction process through which they generate different bands. And here basically the nonlinear dispersion happens, and it is advantageous in terms that it has very high transmittance, and typically they are very robust. However, they add mass and volume to the spacecraft sensor. Generally, they are not preferred that much. Now, one of the important thing is the grating. So grating based spectral dispersion sensor techniques are preferred in our hyperspectral sensors mostly. So this grating also comes in two types. One is the transmission grating, where the input light is there and the separated dispersed light is in different wavelengths are transmitted. And so basically this gratings works in the basic principle of the interference. So we all know this Young's double slit experiment. If the light passes through this slit, there will be a constructive and destructive interference happening into the image plane. So based on the constructive interference, that will be called as a pass band, and where the information will be received. So now as we increase this number of slits, so as we increase, the resolution will become more and more better. So this is how. So based on this interference principle only, these gratings are designed. There will be a large number of groups, multiple slits are present, and they will be diffracting the light, incoming light. Okay. Now there is another type of grating, which is, we call it as a reflection grating. So the input light is there, and the grating will disperse the light in different bands depending upon the number of groups number of slits which are going to put on this grating. So there is another variant which we call it as a blazed grating. Basically, this blazed grating gives us better efficiency in one particular direction. So this is basically, it can be a reflection grating also. Similarly, there is something called prism, which is basically a combination of prism and a grating. So the input light is first passed through a grating, and then it is passed through the prism. So basic advantage happens is, after the grating, the angle of dispersion changes. But if you put another prism, then we can align our dispersed light into the in the angle which is parallel to the incoming light. So this is the advantage of prism-based configuration. There is something called wedge filter-based dispersion, where we vary the thickness of the filter. This is basically a simple interference filter, where we are varying the thickness. So it creates a sort of wedge, and depending upon the thickness of this material, different wavelengths will be passed. So this also acts as a hyperspectral sensor. Many sensors, the compact sensors, adopt this technology. Now the electronically tunable filters are there. These are basically the electronic signals are provided. They are basically liquid crystals or the acousto-optic based crystals. So based on the electronic input, they will pass only one particular wavelength. So the difference between this and the grating based sensor will be, like here, the spectrum will be separated in time domain. So there may be some few milliseconds or microseconds of time gap between one to another spectral sample. But however, in grating case, the spectral samples are generated simultaneously. So this is the key difference. And of course, here we need a lot of electronics and other circuitries to operate these electronically tunable filters. Now, there is another class of dispersion techniques, which is called as Fourier transform spectroscopy. This basically works on the principle of Fourier transform, which is basically interference of two input waves. So basically, any spectrum we can Fourier transform to an interferogram, and also if we record this interferogram, if we do the inverse Fourier transform, we will get the spectrum. So based on this principle, there are two types of interferometers. One is Michelson interferometer, where the interference is generated using one moving mirror in this case. And there is something called Sagnac-based interferometer, where both the mirrors are kept at a constant position, and by passing the rays in two different directions, the interference is created. So if we compare all these dispersion techniques, the prism, grating, and wedge filter and Fourier transform base, so each has their own advantages and disadvantages. I will not go much in detail, but only thing is that majority of the systems which require very large spectral coverage, which requires very large field of view, they go for grating kind of spectral separation technique. Okay, now some of the performance aspects of our hyperspectral sensors are the field of view, which is basically translates into the spatial resolution. Then field of view is the swath, and instantaneous field of view of the spatial resolution, noise equivalent spectral radiance, sampling time, the spectral range, resolution, sampling, and there are some artifacts or the distortion effects that come in picture, which is called a smile and keystone. So we are all aware of this, what the spectral sampling and resolution means. Resolution is something like the 50% points of any resolved target. So we call it as a full wave half maximum. So this is called as resolution. And the distance between two peaks is called the sampling interval. So now coming to the smile and keystone, basically these are the distortion effects which are present on the any spectrometer. And we, as an instrument designer, we try to minimize these distortion effects. So one particular distortion, we call it as a smile or frown. You can see typically this spectral curve, let's say this color red light should have come on this particular line. However, we are seeing there is a bend in this particular line. So some of other pixels in the next subsequent rows also giving this information. So this we call it as a smile effect. The keystone is basically a magnification change with respect to wavelength. So rather than having a square footprint, we are getting a trapezoidal footprint. So this is the keystone effect. Now, this is just to summarize. This is basically the change in scale factor will lead to keystone. So if you can measure this keystone, and this is the smile. So typically we try to keep these effects as less than a pixel kind of behavior in our hyperspectral sensor. The other feature, important parameter is the signal collection capability. So it is all determined by the bandwidth, what kind of bandwidth we are choosing. If our bandwidth is very low, that means we are very fine spectral sampling. If you are doing, the signal collection will reduce. So there are some other techniques through which we need to increase the signal. Okay, so some of the hyperspectral sensors which we have developed is this is airborne imaging spectrometer, which we have flown. We have been flying this from airborne platforms from 1996, and many sorties have happened for this sensor. So similarly, there is airborne imaging spectrometer 2. Basically, this we have developed in-house using a wedge filter-based system, and it provides 4.8 meter spatial resolution from 6 kilometer altitude. And this also has been flown in various airborne flights. This is one of the hyperspectral instrument we have flown in Chandrayaan-1 mission, and also subsequently in IMS-1 and YouthSat, which is basically the Earth-bound missions. So where we have got 64 spectral bands, and the bandwidth is covering from 13 to 20 nanometer, and the spectral range is the Vineer spectral range. And this is some of the images acquired by this hyperspectral sensor of the lunar surface. We can see a lot of hyperspectral information in this particular image. Now there is another sensor we have flown in one dedicated hyperspectral satellite, which we call it as HISIS. So where 30 meter resolution is provided in both Vineer and SWIR spectral range with a swath of 30 kilometer, and they were covering Vineer and SWIR spectral ranges. And there were more than 300 bands in this particular instrument. Similarly, we had one instrument, IIRS, which is operating from a very wide spectral range from 0.8 micron to 5 micron. This also was flown in Chandrayaan-2 mission, and it has given wealth of information about the mineral composition and the presence of water, etc., on the lunar surface. So it was instrumental in detecting the ice signature and in the polar crater regions of Moon. So this is another mission, which is basically this spectrometer we have developed in the thermal infrared range, which was bound for Mars mission. And this is how these parameters are there. It works in the spectral range of 7 to 14 micron. Now we have developed Vineer and SWIR hyperspectral sensor for our geostationary platforms also, which we call it as GISAT 1 and 1A. So basically they will be offering in Vineer 300 meter resolution, and we are getting 191 meter resolution with spectral sampling of 4 to 6 nanometer. Now we have developed many technological elements in our lab, which is basically the Sagnac FTS, also the Michelson FTS that we have developed. Now, if we compare all these instruments, there is one more instrument coming up in recent future. Will be the G20 based environmental sensor, where we will be having VNIR and SWIR spectrometers that will be covering a swath of 1400 kilometer. And the spectral resolution is very, very low. I mean, it is very fine spectral resolution instrument, which is having 0.2 nanometer and 1 nanometer in two different spectral ranges. So as we have talked about all the instruments, these are some of the major applications. We are all aware: the hydrology, disaster, urban mapping, atmospheric sciences, geology, forestry, and national security, fisheries, or agriculture, environment. There are plethora of application of these hyperspectral sensors. And as I was talking about the atmospheric chemistry, these instruments can give us. See, I was talking about the passband, the atmospheric passband observations. By observing this absorption feature, we can know about the atmospheric content. So the atmospheric sensors focus mainly on this absorption bands and try to derive the atmospheric chemistry information. Similarly, we can do sounding where we can generate temperature and humidity profiles by observing these absorption lines of carbon dioxide, ozone, water vapor, and carbon monoxide, etc. So once we know if the concentration in the atmosphere is changing, we will be able to know from which level of atmosphere these signatures are being picked up. So we can do vertical sounding of our atmosphere. So this we are planning in our next INSET 4 generation satellites. Similarly, I talked about the vegetation health monitoring system. By observing this red edge shift, we will be able to tell the health of our plantations. Also, pollution detection can be done. This particular image shows this is a visible image where the nothing can be seen much about the emission. But if you go into hyperspectral sensor, so the methane emission is seen from one of the site, which is basically a dumping site where a lot of methane is generated. So this is another application. Another application is the camouflage detection. This is mainly used in military application, where typically you see camouflage is created by a vegetation cover. So, for example, some missile or some launcher or some truck or some military movements are happening on the ground. So they are camouflaged by, let's say, green color, etc. So, but this camouflage can be created only in the visible region, in the NIR region and IR region. If you can observe the target characteristics, we will be able to determine whether it is a camouflage object or a real object. So this completes my presentation. If there are any questions, we'll be able to take up. Ashok, hope I was audible to all.
Yes, sir, you are audible.
So we can take some questions from the participants, if any.
I have a question.
Yes, sir.
So hyperspectral remote sensing, no, it is from satellites. Is signal collection a problem?
Yes.
So it,
Yeah, please go
can
ahead.
be used only in LEO satellites, or it can be used in geostationary also.
Yeah, it can be used both in LEO and geostationary. Basically, as I talked about, with a very fine spectral resolution, our signal collection capability reduces. Now, but there are other approaches through which we can pump our signal, is by having a binning, like see in hyperspectral sensor. What happens is the spatial resolution is not that important. So we can do spatial binning in the spatial direction. Also, we can do some step and stare, where we can stare at stare at one particular object and increase our signal collection. So basically, by which we call it as SNS, which is step and stare factor. So let's say if I can stay for 5 times on a given ground object, so I'll be able to collect 5 times more signal.
It is
So
like
these are
increasing exposure time, isn't it?
exactly sort of increasing the exposure time. So through which I will be able to collect more signal. So these are some of the techniques we are able to do better SNR.
Yeah, I think the moderator can ask questions based on the questions in chat box.
One question from Sweta is how can hyperspectral data be used to detect the specific plant species or map soil properties?
Yeah, so Shweta, as I explained, we need to know the spectral behavior of these ground targets. So knowing the laboratory characterization of these particular objects, we will be able to detect from the hyperspectral sensor. So basically, we generate hyperspectral library, and that is matched with the ground lab-based data sets. So we will be able to identify these specific plant types also.
Another question from Varsa Rani Chauhan is what wavelength range is shown at the bottom of the slide of hyperspectral imaging?
Yeah, so Varsha, basically we have done hyperspectral sensing in various spectral range, starting from VNIR 400 nanometer to 900 nanometer. This is VNIR range. Then from 900 nanometer to 2.5 micron, which is sphere range. Also, we have developed a hyperspectral sensor operating in LWIR range. And so these are the various spectral ranges where we have developed our hyperspectral sensors.
Another question from Amruta Patil. What are the latest hyperspectral satellite like NMAP and PRISM useful?
What are the latest hyperspectral satellites like INMAP? Okay, this INMAP and PRISMA are basically used for the global coverage of our environmental monitoring satellites. So basically, they try to see the atmosphere, they study atmospheric characteristics and also the ground features, various ground features in the visible to sphere spectral ranges.
And which kind of satellite are working on the hyperspectral imaging and their use in which type of field across India subcontinent?
Yeah, so right now we are having a dedicated hyperspectral satellite, which we call it as HISIS, and on the for Earth observation, and also IIRS as the hyperspectral sensor for Moon orbit, and also in near future we are going to place one geostationary satellite, which we call it as GISat 1A. That will be at 36,000 kilometer, and it will be having a veneer and sphere hyperspectral imaging capability.
And what are major advantage of acoustic optics tunable filter compared to liquid crystal tunable filter in hyperspectral imaging system?
Yeah, basically the Astro optics provide lower power, and similarly, this liquid crystal based systems needs a lot of qualification in terms of onboard usage. So Acosto optics filters offer better advantage in terms of qualifying and their mass size, and also from their resolving power capability also. So Acosto optics filters are better compared to liquid crystal filters. I think most of the questions are covered.
Okay, thank you, sir, for your excellent talk. So now we will go to the next speaker. And
Yeah, thank you.
The moderator may introduce him.
Thank you.
Thank you.
Great. I am Sivansh Dutt Shukla, moderator of current lecture on microwave remote sensing. Sorry, sir, I am audible to everyone? Am I audible?
Yeah, you are audible. Please proceed.
Okay. So, I am moderator of current lecture on microwave remote sensing and synthetic aperture radar. The lecture will be presented by Dr. Dharmendra Pandey, sir, scientist at Space Application Center, ISRO. Dr. Pandey holds BTech in Electronics and Communication Engineering and MTech in RF and Microwave Engineering from IIT Kharagpur and PhD in Microwave Remote Sensing from Banaras Hindu University. He began his career as Senior Design Engineer at Astra Microwave Product Limited, Hyderabad, where he contributed to design and development of RF and microwave systems. Since 2010, he has begun with the Space Application Center, ISRO, Ahmedabad, where he currently serves as a senior scientist with over 16 plus years of experience in remote sensing and geospatial domain. He has led the development of algorithms for geophysical parameters retrieval from microwave remote sensing data with a particular focus on synthetic aperture radar. His work has provided leadership in translating advanced SAR techniques into operational applications for Earth observation. Dr. Pandey has been instrumental in advancing technologies, development and generating value-added products from ISRO microwave SAR missions, including RESAT-1, 1A, C-band SAR, ISRO airborne L and S-band SAR, Chandrayaan-1 mini SAR, and Chandrayaan-2 dual frequency SAR. He is he is a core science team member of upcoming NASA ISRO mission and EOS-04 SAR mission, where he leads algorithm development for operational high-resolution soil moisture retrieval. He has published extensively in peer-reviewed journals and contributed to several scientific reports. His research interests include algorithm development for land bio and geophysical parameters retrieval using polarimetric SAR, microwave radiometers, spectrometers, and GNSSR, along with the simulation and modeling of SAR backscatter for land hydrology and terrestrial applications. Now I request Dharmendra Pandey sir to carry forward with the presentation. Thank you.
Thank you, Shivansh. Am I audible? Just confirm it.
Yes, sir. You are
Yes, sir, you are.
Yeah,
Yes, sir.
thank you, Shivansh, for the introduction. And I'm very thankful to ISRO Headquarter and IIRS team for giving this opportunity to share my lecture on the micro remote sensing and synthetic aperture radar. Today, I will be more focusing on the different aspect of the remote sensing, which is called microwave bands, and specifically on the synthetic aperture radar. So, as our previous speaker already has extensively elaborated on the optical and hyperspectral imaging, which has a very great applications. Now, I will take up this opportunity to introduce about the microwave, how microwave is going to benefit the our societal benefits and applications. So, this is my outline for the talk. I will be covering on the basics of electromagnetic spectrum and microwave and more basic on the radar basics, how radar works, and the basic principles. I will also touch upon the microwave sensor types, and then the key focus area is the radar and synthetic aperture radar. How synthetic aperture radar is different from normal radar, and how this SAR, what we call it, synthetic aperture radar, what kind of observers are available, and how what are the factors which affect the SAR signatures, and how it is being used as a remote sensing for the environmental and the different land applications. And also, I will also be covering different applications which is getting benefit from the SAR. And then from ISRO side, I will also touch upon the major space-bound SAR missions with a special focus on the our ISRO own A04, which is called RS-1A, Radar Imaging Satellite 1 mission, and NISR, NASA ISRO SAR missions, which is the current mission going on mission. And the last also, as the radar is one of the key remote sensing tools for the planetary missions. I will be also touch upon this SAR planetary missions where we have done very good work from ISRO. We have demonstrated the Chandrayaan-2 dual frequency SAR, and also what science we are doing from the some key results what we have been accomplished from the SAR planetary mission Chandrayaan-2. So let's start with the electromagnetic spectrum. So already, I think I assume that a previous speaker already has covered this section, but I will just touch upon the specific this electromagnetic spectrum, which is the covering the multiple bands, starting from X-rays, ultraviolet, visible infrared, and as today I will be more focusing on the microwave. Basically, microwave is one of the special band in the electromagnetic spectrum, where the atmospheric has a very low opacity. So the microwave has the advantage of having the across the atmospheric. There's no effect of atmospheric over the microwave bands. That's why we call it all-weather satellite from the microwave bands. And if you see in the microwave, basically microwaves are categorized in multiple bands. So basically, there are different frequency bands are there. The last in the bottom table showing multiple bands, what we call it a different nomenclature. So these bands are very have a different signatures and is suitable for multiple applications. So starting from the K band, we call it from the P band, L band, S, C, X, KU, and K band. So these are the major bands, and these bands have basically different frequency range in gigahertz and different wavelengths. So the major advantage of microwave is that it penetrates in the atmosphere, and it has a longer wavelength, and it has a multiple applications. So I will just go through them. So let me start with the radar basics. So basically in the radar, typically it has a system which has a transmitter and receiver with some antenna part, and this radar basically it transmit a signal, kind of, it transmit a radio electromagnetic pulse from the antenna. So if you assume this antenna is a kind of flashlight, so you are transmitting a signal which is passing through the uh, clouds, passing through the clouds. And but if there is a cloud, the optical and other hyperspectral sensor doesn't work actually, because it has a very high frequencies. But in case of microwave, it will penetrate to the clouds, and the clouds, then there will be reflections from the targets. In the bottom there is targets, and this antenna will receive the signal, reflected signal from the targets, and then the receiver will receive the signal and do the processing and record the data. So if you see the basic element of radar is that there will be a transmitter which generates a high power microwave pulses, and there will be a circulator, the switch, which will switch between transmitter and receiver, and there will be an antenna. There's the antenna which radiates the transmitting pulse towards the scene and intercepts the power of that spectral pulses. So this is the typical radar basics, where radar functioning operation building blocks, which shows this how radar works. So this is kind of a reflections we got. These blue curves showing the transmitting pulses, and then the red curves showing the reflected pulses from the targets. So when we receive the targets, we process the data to see how to detect the target in a particular way. Now, in the fundamental of SAR remote sensing, basically there are multiple silent features of sensitive aperture radar. The first is very important, high spatial resolution. So we can have a very high resolution images, SAR radar images from the SAR, and it has a all weather and all day measurements capability, because in all weather means it has very low impact from the clouds and weather atmosphere, and because it has its own source, it doesn't depend on the sun, as in the case of optical and hyperspectral, where the major depending on the sun, so you cannot imagine the night. But in radars, they can operate in the night also, so that's why we call it all day and all weather measurement capability. The microwave is very sensitive towards the dielectric properties and water content in the soil. So that is one of the very key silent features. It has a deeper penetration depth in the vegetation and soil due to microwave plants. So basically, in case of the very uh, uh, different targets, especially the forest, suppose in case of forest, the microwave can sense the forest also area in this case. And it has a multi-polarization modes for improved applications. So I will go one by one. So just to graphically, I will show you how the SAR remote sensing works actually. So basically, it transmits a signal. This is the one case where the soil is dry. Just bottom stage, you see the figure. This is a very dry field where we are having the measurements, and this is a cloud field basically. So there is a very less soil moisture, and there is no crop. So low soil moisture is low nitric constant, and if you transmit a signal which is shown by the black line, the energy get reflected. Uh, Very less amount of energy get reflected back to the sensor, and most of the energy getting forward actually, because of the low soil moisture. But in other case, if the soil get wet, the energy which is getting reflected from the soil is becomes more actually. So simpler, there's a thumb rule is that the moisture content, which is basically driven by the dielectric properties, the microwave basically is highly sensible towards the dielectric properties. So these are the two typical cases where I want to highlight this, how microwave sensor to the soil moisture and how it measures the reflected energy. Now, this is a typical example of in microwave also we have a active and passive kind of sensors. So basically, in passive sensors we do not have any source at the satellite, and we depend on the sun or maybe thermal another so the source of radiation is the sun. And in case of active sensors, which is called as SAR, temperature radar, where we have its own transmitter and receiver both. So we do not depend on the any kind of third source for the transmitting. And when it is the active sensor basically transmit a signal, and then we call it a return to pulse, and they get the detect the targets in the. So this is a typical example of having two kind of sensors, active and passive. There is a gamut of multiple combination of active sensors and passive sensors in the microwave domain also. This is a typical example on the left side. I just want to show you the building blocks of the radar. Basically, active sensors. So, active sensors means there will be a transmitter as well as a receiver, and then the transmitter will transmit a signal through the antenna. It will radiate, and then there will be a reflection that will be received by the receiving. So there will be a transmitter and receiver both in case of active. And there is a kind of passive sensor where which will receive the emissions, the natural emissions from the targets. It doesn't have any kind of a active sensors. So basically, so in the active sensors we have a real aperture radars, we have a sensory aperture radar, a spectrometer, altimeter, and ground peak radar. So each of the radar have different functions, different applications. Today I will be more talk about the more focusing on the more on the sensory aperture radar, which provides the very high resolution images for the different applications. So what is radar actually? So if we explain very briefly what is radar, basically it's a microwave energy transmitted from the source, and then the scattered energy from the target is being received by the receiver. So this is what actually. If you in the left bottom you say there's a there's a radar which transmits a blue pulses, and there's a target which reflect a lot of energy, and the energy is coming back to the sensor, which is received by the radar, and then the signal get is transmitted to the ground stations. So basically, we typically measure the time delay between the transmit and receive, which gives a range difference. So basically, we are measuring the range. That's why classically it is called radar, radio detection and ranging. So basically, the one of the first principle is that we are trying to detect the ranging, so how much distance is there from the transmitter to the target. And if you talk about the SAR, sensing aperture radar, which is the one of the advanced version of radar, basically, so earlier radars are basically real aperture radar, where the resolution was very coarse in kilometers, and this synthetic aperture basically comes when we have a longer antenna. Basically, typically, if you want to have a high resolution from the normal radar, it is not possible because you need a very longer antenna length to get a meter scale resolution of images. So what we do, there was a centrifugal aperture radar was invented in the almost during the Second World War, and by Doppler processing, we can improve the resolution in terms of the meters scale. So this is one of the animation I want to show you that how SAR is being imaged over the particular area. So this is a satellite. There's a satellite, SAR satellite. Micro satellite is moving in the direction of a long track, and it is seeing. It's always side-looking radar. So basically, it's saying it is looking at the right side of the satellite direction, and as it moves, it is creating the transmitting signal and getting back to the receiver. So all the signals by signal processing, we are getting the image action. So basically, sensing aperture radar provides a 2D high resolution images, which is not possible from the normal radar actually. So this is the kind of animation again play. You can see how the image is being formed over the particular area. So this is the basic way how the satellite is the data is being collected over the area by the microwave satellites. Now, when we say the microwave sensor, basically, as in case of optical and hyperspectral, that they measure the radiance actually. But in the case of microwave sensor, basically we call it a SAR backscatter. What is the observable? So basically, what we see from the sensing aperture radar. So the SAR backscatter is the kind of measure of reflectivity of the surface. So it is basically measuring the how much energy is getting back to the sensor. depending on the target property. So this is a typical example of the forest area. The schematic diagram shows the forest with the canopy in the green colors, and then there's a trunk and there's a ground. So whenever the SAR sees, it sees the total backscatter from the multiple components, the reflection from the crown, we call it a canopy, and then reflection from the trunk as well as the ground. So once you see the total backscatter coming from the target, it is a summation of all three components. So if you decouple all these components, there are multiple components which makes the total backscatter, which is being measured by the SAR, centimeter aperture radar. And there are now the next slide. I just want to explain what are the factors which affect the microsignatures. The microsignatures, basically, there are two kind of target factors which affect. One is the sensor parameters, which is basically depend on the frequency, at what frequency we are working, whether it is lower frequency or higher frequency. Then the incidence angle also matters, which is important, and then polarization. These are the sensor parameters. And in the target properties, actually, basically it depends on the surface properties and land cover. So in the surface properties, basically it is mainly driven by the kinetic properties as well as the surface roughness and the vegetation part. So these are the major factors which govern the which modulate the SAR signature. So whenever we are going to go for interpretation of the SAR signature, we need to understand, okay, what kind of targets are there in the ground, what kind of reflection we expect from the particular targets. So this kind of understanding gives a very good insight into the signatures analysis. Now, there's a very good concept in the SAR basics is the polarization actually. So in the electronegative wave, basically the electronegative wave, the microwave signals are polarized. So when we transmit a signal, we transmit with a particular polarization, whether it is horizontal or vertical. So when we transmit polarization in H polarization and we receive in polarization, we call it HH. The first letter shows the transmission, and second letter shows the receiving in which process are receiving. So there are multiple combinations. We have HH, HV, VVH, and VV. So each combinations have a different details. So this is the kind of first image. In the left side is showing the HH image. Basically, we transmit an H polarization, H horizontal polarization, and then receive in H polarization. So you see what kind of signatures are there. So this is an example of SAR images in different polarization. So this is the left, the bottom left, the left is the HH polarization. Then we have a cross polarization, H and V. We transmit in H polarization and we receive in V polarization. So basically we call it a cross polarization basically. And in the third one is the VV polarization. We transmit in V polarization and we receive in V polarization. So, so if you want to make a kind of a color composite similar to optical and hyperspectral images, similar we can make three combinations and we can get the RGB. We call it red, green, blue channels, and then we can get a RGB color image from these SAR images also. This is called a false color composite, where we assign three channels to the three different colors, and then we get a very good color. So these color composites are very quite good and optimal for the better interpretation of the targets and the classification. Like this is a scene of the Bombay region, region, Mumbai, and then you see that this is the ocean part. The blue color is mostly ocean part, and these are the urban area, which is a very high backscatter zone. And there is a airport also there, which is kind of very surface scattering is there. So I'll explain how. So the major challenge is that the how to interpret these SAR signatures to understand the what kind of targets are there on the ground. So this is just an analogy with respect to the optical images. So in the right side, basically we have a IIRS P6 least 3 data. It's a color composite. The most of the red colors are basically vegetation in the optical images. In the left part, we have made a same area is being mapped by the LS Parker to L band data, which is kind of color image. And if you see the green color, basically most of the green colors are basically vegetation and the forest area. And there are mangroves are there in the coastal area of the mangrove Mumbai area, and these are the very high targets of urban area. Basically, these are the mainly man-made structures, buildings, and settlements. So those are call it very high backscatter zones. Similar to this, one of the image where on the left portion, I want to show you the polarimetric colorful image from the radar image, and then the right side is the optical image. You should see same Dehradun city we have mapped using the SAR and the optical, and there's a very good analogy and good understanding for the interpretation point of view. These are the mostly forest area, which is basically in the red color, mostly call it because of high NDVI, high vegetation part, and then there's a green color is the forest. So if you want to understand properly the SAR image analysis, basically you should also know how to go for interpretation to understand the scattering mechanism, because the microwave basically is driven by the scattering properties. So in order to do that, I'm just going to explain briefly about the uh, how to how to interpret this. So basically, in the SAR we have H and B polarization. So basically, the microwave is mainly driven by the scatterers, actually, different kind of scatterers in the surface. So this is kind of like if you have a dielectric constant, moist and dry, it varies depending on this dielectric constant. So in the left side, if you see the dielectric constant, basically one of the driving factors for the microsignatures. For the water, we have the number is 20, which is very high. And then the rest of the targets are basically rock, soil, and vegetation is kind of very low, like around 10. So there's a huge window for that where the microwave changes with respect to this dielectric constant. Now, there are three major scattering mechanisms happening, which is basically mainly responsible for the SAR signature. One is called surface scattering, which is normally generally represented by the blue color, and double bounce scattering and volume scattering. So basically, volume scattering means whenever there is a volume kind of medium is there, kind of forest is there, kind of crops are there, we have a volume scattering. And then there is a flat surfaces there, we can have a surface scattering. So this is the typical example of the what is the SAR typical signature looks like. So basically, we can decompose the whole radar basket in three major parts. One is the surface scattering. So basically, in the smooth water kind of structures, smooth, there's no roughness, smooth surface water gives a low return basically, and it is called surface scattering because low return means when you transmit a signal, most of the energy doesn't come back to the SAR. It's actually going back to the forward direction. So you have a very low return and the kind of radar return. In case of volume scattering, whenever there's a vegetation in terms of forest and thing, a lot of volume scattering happens. So that gives a moderate return actually. So and the last one, which is very important, is that the urban area. So basically, all the structures, all the man-made structures, bodies, they give a very high radar basket actually because they have a very good. They basically driven by the double bounce. So whenever you transmit a signal, there will be two bounds are there. Then it will be so basically what is happening in the urban area kind of structure that the basketer get enhanced. So that enhancement gives a very peculiar signature to the urban and man-made structures. So if you understand this basic scattering mechanism, it will be very helpful to understand the and it will be very helpful for to interpret the SAR images. This is one of the example where I will to show you the importance of spatial resolution. So this the left side is the SAR images over the Giza pyramid area. So if you see, this is the 20 meter is not very good. You are not able to identify the different structures, but still, this is a grayscale image where you get a high grayscale and high bright targets. And if you have a high resolution data, like 1 meter resolution from TerraSAR X, that is X-band SAR images, you see a lot of bright features are there. So these bright features basically kind of a structures are there. The man-made structure or the kind of structure which gives a very enhanced radar basket to the sensor. And there are some dark areas there, which is mostly kind of the radar slope and then the low return are there. So basically, SAR image is kind of combinations of high return and low return and the medium returns. This is the example of where I want to just focus on to understand, to explain you about the multi-frequency, how the frequency plays a role. What is the role of frequency in the target selection? So this is one of the examples where we have a multi-frequency SAR images from the same platform. And you see, same area is being mapped by three frequencies, X band, S band, and L band. And this is the interpretation of the image, where the X band, most of the X band, because it is a high frequency, it is going to interact with mostly leaves and twigs and small branches. And if you go to the C band, it is mostly the mid crown and canopy. And L band have a deeper penetration because it's a longer wavelength. It will go and interact with the mostly primary and secondary branches, trunks and ground in the forest area. And if you take the largest band is the P band, which is the very longer wavelength. around 70 to 80 centimeter. It will go and impact it not only from the forest and trunk, the canopy and trunk, it will go up to the ground also. So this is simple one target. If you see the same forest area, this is the forest area. If you see there's a very clear difference between the X band, the SAR signatures, S band and L band. At L band, most of the you are seeing a very good. No, the in X band you are seeing only the canopy signatures, but in L band, because for deeper penetration, you are getting very good dynamic range and very good contrast as compared to S band. So each band has a different applications. Some of the applications are basically met by the X band, and we have multiple applications from L band. So the frequency of operations is very important once you go for the kind of applications you are targeting. Now, this is the apart from the frequency, the radar penetration depth. I want to show you how it varies with the different kind of targets. So, if you have a vegetation where already I explained you in the previous slide that X band mostly is situated with the top canopy, and the L band, whether the L band is go and map the whole canopy, in fact, with the whole canopy. If you take the like a dry snow and dry sand, so again the L band having deeper penetration because of the longer wavelength. So the microwave has a very good capability to go deeper up to the different depth of the targets, which is not available in any other band actually. In the right side, I just want to show you the effect of roughness. So roughness plays a very important in the SAR signatures. So if you transmit a SAR signatures, SAR reflection, SAR EM pulse from targets, and then if the surface is smooth, which is kind of no specular reflection, so most of the energy will go back in the forward direction. So this is the forward direction. But if you have a roughness in the slightly rough surface, some of the energy will go back to the backward direction. This is called backscatter. And if you have a very rough surface where the major contribution coming from the diffuse reflections, basically you'll get very high radar backscatter as compared to smooth surface. So surface roughness plays a very important role to enhance the backscatter in terms of the classifications and applications. The next parameter factors, which is one of the key factors, is the dielectric properties. So basically, microwave sinusoidal is basically based on the large contrast between dielectric properties of dry soil and water. So if you see the dielectric properties is the properties of material which influence under any electromagnetic field effect. Okay, so if you see the dielectric properties of the soil is basically a mixture of dielectric constituents, and it also depends on the frequency, temperature, and salinity. So the right side we are showing this relation that if you have a high soil moisture, you have a high dielectric constant. So this is the one of the factors which govern these SAR signatures. So if you have a dry soil, you have a low signatures, and if you have a high soil moisture, the dielectric constant will be more, and then correspondingly the signature will be high, more reflection. This is one of the synaptic view of the what I have already explained. Is that if you have an incident wave, so there is an automatic wave incident on the target, which is the low soil moisture content. So most of the energy will go back to the forward direction. Very small amount of energy is going back to the sensor. But if you have a moist soil, so dielectric constant will be high, and then you have a more microwave energy, which is going back to the incident wave, a kind of reflection wave actually. So with increasing soil moisture, the dielectric constant of the soil is increasing, and then that leads to a enhanced radar backscatter also towards the sensor. So this is the basic typical behavior of the dependently on the moisture on the SAR signature. Now, that was a part of the what is the SAR and what are the factors it depends. Now I will be touching more about what kind of applications we are doing. So this is one of the key area where we are utilizing this centric aperture radar images for making the benefit of all the societal applications. So we are from ISRO, we are involved multiple applications. We are doing multiple applications with our data, and I will go and just briefly cover one by one. And there are few applications I want to mention here, and there are more are there, but I will touch upon some key applications, which is basically driven by the microwave SAR. So the first application, which is the applications of SAR in agriculture monitoring. So as you know, in the Indian context, we have a monsoon season, almost more than 3 and 4 months, and that is the monsoon season. Basically, the optical and other sensors doesn't uh, are not able to see the ground because of the cloudy conditions and the very huge rainfall. So what happened during this monsoon season? The only one options we have is the microwave. So microwave signature, as I told you, the microwave has the capability to observe the targets and agriculture fields during monsoon season also. So this is one of the examples where we use the SAR data sets, SAR images to identification of paddy crops. So this is the example. This is the field photographs where the field is mostly summer paddy in the Karnataka region, Karnataka, India. And you see the red colors, basically the RGB image, which is showing the color composite of them. And these red colors are basically is the paddy, summer paddy in the Karnataka region. So why the red colors there? Because it's a very high basketer, enhancing basketer in the RH channel. So the reason is that the paddy has a very unique crop phenology. It has as a background, it has a very water level. So because of the the water has a very low basket region, and then there is a crop which is coming from the water. So there will be a double bounce kind of scenario. So this double bounce makes a very unique signature of rice in this case of mapping through the SAR remote sensing. So SAR remote sensing is one of the optimum sensor which can map the rice fields without depending on the other sensor. This is another example of where I want to show you the example where we have mapped the classified the we have derived the transplantation dates using multi-temporal SAR data. So basically, the transplantation date is quite important for to know how much area is being sown. And then we have also derived the biomass map. So biomass, basically in the crop biomass, basically we are looking for the what will the yield at the end of the season of the crop season. So basically here, this is the here they have used the RISET1 data, 1A data to map this area rice plantation, transplantation in Gangetic West Bengal region. And there's another applications where we do the crop classification. So this crop classification is very important because you want to know the what type of crops has been shown and has been grown over the field. So this R is one of the key remote sensing data which gives you the very good classifications if you have a multi-frequency SAR data. So this is one of the example where we have shown the multi-frequency SAR data to classify the crops. And we got multiple crops, including other land use and cover pieces. Another example is that which is very, very important from the especially in the during monsoon season because of the heavy rainfall and very untimely extreme conditions. We got a lot of area is getting flooded. The flood is one of the India is a highly prone flood disasters by the disasters prone area actually. So here the SAR data basically is one of the tool, and you can say like a data sets which can map the flooded area, especially the water bodies. So, including the water bodies, if there is a flood, actually, most of the land use land cover are getting flooded by the water bodies. So, in the water signatures are very huge, very important. So, in the right side, if you see, this is the FCC image of three SAR data images are there, having flood, and all the blue portion are basically flooded, the black portion. So, all the severe flooded areas are very important to map because during these flooding situations, the decision makers, especially the different stakeholders from state government and central government, they want to know how much area is getting affected by this flood. So we need to provide this large area mapping very quickly actually, so that the rehabilitation or maybe this kind of decision has been made to go for rescue and rescue operations. So this is one of the key applications of the SAR inundation mapping. Similar way, this is one of the example where we want to show how we are using SAR data for mapping the changes into the water spread from water spread. So this is one of the nuts where we use this thing, and then this is so every time we can map this area how much water area has been spread and changes. So all the reservoir, especially over India, we can map and the temporal changes has been mapped with the SAR data. This is one of the example where we want to show you the DEFA data has been used to derive the soil moisture. This is one of the key essential parameter for the agriculture applications because all the crop growth and crop yield depend on the soil moisture conditions. So we have used the soil moisture estimation at a very high resolution with this data. Another example application is the forest biomass. So forest biomass is one of the very, the essential climate variables where we use the forest biomass to understand the link with the climate change. So forest biomass has been derived from the L-band SAR data. Another key applications is the snow and glaciers. So the SAR data is one of the key area to identify the dry and wet snow in the Western Himalayas. This is the Western Himalayas, the DNSAR. And another example is the coastal and ocean application. So these are the applications where the SAR data plays a very important role. And so I have shown that some key applications. Now I want to show you some of the major spaceborne SAR missions, which having the multiple. So in India, especially in ISRO, we have a RZ-1 series, and currently RZ-1A is in orbit, and now we're going to have a multiple SARs in the coming missions. And in the planetary also, we have a mini SAR. Chandrayaan-1 mini SAR data was there, and Chandrayaan-2 is the DXR, where SAR is playing a very important role for planetary radar remote sensing. Apart from that, and so I'll show you this one of the IIRS-ISRO, which is this is the lab picture from the front. This is the antenna, 6 by 2 meter antenna of the RZ-1A, which was launched in June, February 2022. So the pictures I was just want to show you in the lab how the satellite is being integrated and tested in the different phase of the mission. Some of the these are some of the radar images, SAR images, and polarimetric images have been collected over different land use, land cover, and different targets, including the forest area, mountain areas, mangroves, and different globally also we have mapped different areas. Now, the current mission, what we have been working on the NISR mission, which is one of the first global Earth observatories having 2 frequency, 12 frequency radar. It's a L-band and S-band radar. The S-band is being designed by and developed by the SAC ISRO, and L-band is designed by the JPL NASA. So this is the first kind of radar, basically, which provides the very high resolution SAR images, as well as the very high polarimetric and interferometric capability. And we have, this is one of the some images I want to show you, which is being targeted by the NISR mission. I may not go into detail of that, but we are covering from the ecosystem, forest agriculture, hydrology and soil moisture, solid earth, cryosphere applications, coastal and ocean applications, and natural hazard and disaster. So these are applications correctly being addressed by the NISR mission. Apart from the Earth observations, I just want to I want to cover this Chandrayaan-2 DXR, which is one of the first 12 frequency SAR in Chandrayaan-2, especially for mapping the lunar surface, which is the polar regions where we are expecting the water ice in the polar region. So these are some of the science outcomes from the Chandrayaan-2, where we have mapped the polar regions to identify the polar planetary ice detections, and large number of geomorphological craters have been mapped. And still the data it is providing very good amount of data sets. So all the community, they can use the data sets to further R&D and science. This is so this is the end of my slide, where still we have a lot of remote sensing, SAR remote sensing applications being covered. And thank you. So so this is the end of my slide. If any questions are there, please.
Thank you, sir, for very insightful lecture on microwave remote sensing and synthetic aperture radar. So we have few questions.
Yeah.
So Divyansh Gupta, why does water appears very dark in SAR images while forest appear bright?
Okay, I think this is one of the very primitive question and very good question. So basically, in the water, as I explained you, the water has a very high dietary constant, and the most of whenever you transmit a signal in the so very less energy is getting back to the center. That's why. If you have a forest in any area, it has a volume scattering. So a lot of scattering happens, and then the scattering gets enhanced. So because of volume scattering, you get higher backscatter as compared to water. So if you see very simple radar images, you'll see some dark tones and some high bright targets. So most of the dark tone basically is being explained by the smooth surface, and then low dietary constant area. Actually. So similar to water, if you see the any air strips also, the air strips have very smooth surface. So you will see very dark airport in this is the airport in the images also. So that is the reason why we have a low base factor from water and high base factor from forest area.
Yes, sir. The next question from Shobhana. Can microwave radar tell us how much water is in the soil deep down or only on the surface?
Very good question. So basically, as of now, we have a L band. So basically, to know the how much moisture is there in the water in the soil, basically you need to have at least deeper penetration depth of more than 10 centimeters. So current as of now, like from example from NISR data, NISR mission, we are targeting surface soil moisture up to depth of 10 centimeters from the we can detect the moisture availability within a soil. If you want to have more deeper depth, basically, currently, technically it is possible, but it's because we do not have P band SAR, which can deeper, we can see the deeper in the depth of more than 50 centimeters. Currently, there's a biomass mission is there from the ISA, European Space Agency, that is in operational. And that data still we can see up to the 30 centimeters, 40 centimeter depth of soil. You can see the water, how much water is there in the soil to depth of 30, 40. And if you want to very low frequency, longer wavelength SAR. Maybe you have to go below P-band SAR, which is still not in as a space borne. So yeah, it is possible to address the quantify the amount of water in this soil at a deeper depth, subject to the availability of the SAR.
Okay, sir. Sir, next question from Arya Bhardwaj. Sir, at ground we use many radio and microwave frequency antennas in telecommunication, etc. Will those interfere with LP band of SAR?
Yes, I think yeah, absolutely right. I think these ground-based transmitters within a similar frequency, definitely they create a no, we call it a radar radio frequency interference actually. So like there was example from the other mission ground-based transmitters. So yes, they create a problem when you observe the same Earth from the space. If you transmit L-band signal and then you have on the ground you have L-band transmitters, it may interfere with the radar-based observations actually. Yeah. So what we do actually in order to cater to that, we definitely we develop a methods to identify those RFI interference points and then mitigate those effects actually. So there are ways actually. That way, by that way, we can address this RFI interference on the ground.
Okay, sir. Next question from Ritesh Kumar Sharma. What is the difference between GPR and radar, and which is best, GPR or radar?
Okay. So actually, GPR is a family of radar. Radar is actually superset of radio detection ranging. So GPR is a kind of radar, but GPR radar. So ground penetrating radar basically it works in a near field, and close to the. So it is a low frequency radar which will penetrate to the ground, to the deeper depending on the frequency. So normally GPR frequency range is around no starting from 6 megahertz to the 100 megahertz and 500 megahertz. So depending on your applications. So like typically GPR is currently in civilian applications. The GPR is being used to map the urban utilities, especially the underground tunnels, underground areas. So basically the typical frequency is 100 megahertz. So GPR is also part of radar actually. It's a radar. So radar is the superset, but GPR is a family of the radar actually.
Okay, sir. Next question from Vani Ramesh. How SAR help for land cover classification compared to optical, and which one is better for land cover classification?
Okay. So land cover classification is concerned, basically there is no single sensor which gives you the all the best classification accuracy. But nowadays, if you terms of suppose if you want to do the classification during monsoon season, okay, so that time optical and hyperspectral may not work. You have to depend on the only on the SAR remote sensor data sets. nowadays what happening in the scientific community, they are moving towards the multi-frequency, or maybe you can say multi-satellite fusion. So now people are trying with the SAR and optical fusion actually. So whenever the SAR works better, you get advantage of SAR, and whenever the optical works better, you get the advantage of both. So now the whole community is moving towards the multi-satellite fusion. So I would say the best solution is that multi-satellite fusion instead of having one either satellite or either SAR or either optical fusion, because both of having their own their own problem area.
Yes, sir. One last question from Shweta. Why is L-band radar more suitable for vegetation and forest studies?
So as Sweta, as I explained you, the frequency of operation is quite important. If you have a lower frequency, like kind of a L band, so C band, what happens? C band or maybe kind of below the S band. As you go higher frequency, the wavelength get reduced. Okay, so as I explained in the slide, this slide, maybe just to quickly, I will go through this slide where I was explaining this interaction. So actually, this yeah, right, this one. So as you see, it is the C band. Basically, if you have a smaller wavelength than L band, you most of the interaction scattering will happen here actually. So you will get less energy from deeper depth. So that's disturbance zone. The L band is most stable because C band will get saturated. You cannot differentiate. The detectability will become very less as compared to L band if you go X band or C band. So that's why most of the applications of the forest biomass, forest disturbance zone mapping, we prefer longer wavelength. L band data is most optimal as compared to C band because the higher frequency get the C band X band gets saturated actually. So there is a saturation where you cannot differentiate the signal and noise actually. That is the reason.
Thank you, sir. That is the last question. And thank you for very insightful lecture. This session clearly explains how SAR works and how various factors influence SAR backscatter signature. We also saw wide range of SAR application in Earth observation and environmental monitoring. The overview of major missions such as EOS-04 NISAR and SAR instrument on Chandrayaan missions highlighted the growing importance of radar technology in both Earth and planetary studies. On behalf of everyone, I sincerely thank Sir for sharing such valuable insight with us. Thank you.
Thank you. Thank you so much, Shivans, and also thank you so much, ISRO headquarters as well as the IRS team for giving this opportunity. Thank you so much.
I thank both the speakers for their excellent presentation. So with this, we come to the end of today's session.